Hello, Calculus 2, Math 1342. This is extra practice for Quiz 6. Quiz 6 covers work, that's section 3.9, and then we move into the multivariable textbook with sections 1.2, 1.3, and 1.4. We will get started now. Number 1, we are pumping gasoline out of this tank. This picture won't be given to you. I just have a pre-drawn, then we will fill things in as we read the problem. But we see this is an inverted right circular cone. It tells us the vertex pointing down. It tells us the base is at the top. The height is 21 feet and base radius is 7 feet. It's filled to a depth of 14 feet with gasoline. And then we're told how much the gasoline weighs. We want to find an integral that calculates the work required to pump the gasoline through about 4 feet above the tank. The first thing that we notice before we do anything else is we are in US customary here for our units. That's important in our setup. Now I will start labeling based on the problem. The way I always set these up, I always put 0 at the bottom. This is the way my world is oriented. And then the total height of the tank is 21 feet. So that would go here. And then we have a spout, which is 4 feet above, and 21 plus 4 is 25. So that goes here. I'm also told the radius is 7 feet. Let me draw a radius here. This is 7 feet. And then one more thing I'm told is it's filled to a depth of 14 feet. So let me draw that here. 14 is maybe here. My gasoline will be this peach color, but this is what it's filled to, 14 feet. Just like this. Wonderful. Now we're ready to start working on the problem. What I want to do is have some height y in here. And I think about the work just for this slice. So let's slice this and thicken. And this will be thickness delta y. And let's write this down, the work for this slice. Well, we begin with how much it weighs. This is US customary. So acceleration due to gravity is already a part of this. This is not a true density. Sometimes we refer to this as a weight density, but we will make sure we have all the pieces because we will check our units. So this is pounds per feet cubed. Now let's multiply by a volume. My slice will have its own radius, r, and so the volume is pi r squared. That's the area of the circle, and then times delta y. Now this is a volume. This is feet cubed. So you notice so far I have pounds, I have a force. All I need to do to get work is multiply by the distance that this slice travels. It's sitting at height y, and we need to go all the way to the top of the spout. And so this slice travels 25 minus y. 25 minus y. And this is in feet. And you notice altogether we have foot-pounds, we have our unit of work in US customary. So I have all of the pieces. But you notice so far it's not complete because I have an r here and I need to write r in terms of y. So let me draw this vertical line here, and then I'm just going to redraw this triangle below. We're going to need to use similar triangles here. So I have this bigger triangle. Inside it, I have a smaller triangle. And then I can start labeling things. This is my radius of the base. This is my r. Maybe I will color this in pink down here. This is y. That is the height. And then the height of the entire triangle is the height of my tank, which is 21. Here's where we set up similar triangles. We have 7 over 21 equals r over y. And for example, I can just multiply through by y. We get r 7 over 21 is 1/3. So I get r is y over 3. This is what I want to use. But now I'm ready to just immediately write down my integral. We have 47 pi, and then we found r as a function of y. R is y over 3, and then squared, 25 minus y. This delta y, really this was Riemann sum notation, but when we go to the corresponding definite integral, the delta y becomes dy. Now the only thing left here are my limits of integration. This I integrate over where my gasoline is, and my gasoline, you see, ranges between 0 and 14. So I integrate 0 to 14, and this altogether is in foot-pounds. This is our answer here. This is a setup only problem, and so we leave our answer just like this. There's no need to simplify the integral or evaluate the integral. This one's very similar, except I changed a lot of things. It really makes us think about setting up these integrals by changing some things. So this time the vertex is pointing up, and I have a square base. The height is 100. Let me just start labeling as we read the problem. As you know, I always put 0 at the bottom, and so my height 100 would be up here, and the width at the base is 40. So let me denote that down here, perhaps. This is 40 meters. Meters. We are in metric. That's another important comment here. Then we keep reading. It's filled to 80 meters. So maybe this is 80. And let me color in my liquid again. This would go up to here. I'm given the density of my liquid in the problem. And then the final thing, there's no spout at the top. We just find an integral that calculates the work required to pump to the top of the tank. So I begin very similar. Now this one, because it is metric, maybe I will remind you of some formulas. We have work is force times distance. Force is mass times acceleration, and mass is density times volume. And we're going to use all of this here. As before, what I want to do is slice, and I have drawn it here, although it's not perfect. What this is a square thickened by delta y. And the slice is sitting at height y. And we can calculate the work for just this slice. And then we will write down the integral to calculate the total work. So here, maybe I'll call this length, say, L, it's fine. And the slice, well, let's start at the bottom. You see, thinking about these formulas, we start off with density, which is 1,020. And then we multiply by volume. Here, we have a square and then thickened by delta y. So the volume is length squared delta y. Now let's write our units underneath to check, just like we did before. We have kilograms per meter cubed, and this one is meters cubed. So far, we have a kilograms. This is a mass. Now multiply by acceleration. This is 9.8. This is meters per second squared. So far, you see this part, we have kilogram meters per second squared. This is a Newton. So we have Newton, and this is our measure of force. The last thing we multiply is by a distance. Then we will have the right units. We will have a work here. And we are sitting at height y. We want to pump to the top. The distance is 100 minus y. And this is in meters. And so you see, we have Newton meters, we have joules. But just like before, we need to get this L, the side of this square, written in terms of y. And similarly, just like before, we can use similar triangles. So let me draw it like this and like this. This is L. This is 40. And then my total height is 100. But the height of this little triangle here is not Y. You see down here is Y. Down here is Y. And so this part, which will be in my similar triangles, 100 minus Y. 100 minus Y. Now I'm ready to write down the correct equality of ratios coming from similar triangles. Well, this is the base, and the base divided by this height. So let me write that down. L divided by the height, 100 minus Y, would be equal to this base divided by this height. So 40 divided by 100. This is the setup. Now I'm trying to solve L in terms of Y, and so I can just multiply through. We have L is, well, 40 over 100 is the same as 4 over 10, which is 2 over 5. So I have 2 over 5 times 100 minus Y, which is, let's see, 40 minus 2/5 Y. This is what we wanted here. So I'm ready to finish the problem. I'm ready to write down my total work as a definite integral. Maybe I'll do this here. My total work, we would have 1020. We would have 40 minus 2 over 5 Y squared. We have 9.8. We have 100 minus Y. And then dy. Finally, my integral, or my liquid, lives between 0 and 80. And so my limits of integration are 0 and 80. And this is in metric. So this is in joules. In fact, I checked my units when I wrote down the work for a slice. And so this is number 2. Number 3, this one involves a spring, and this is still section 3.9. You will notice this is much shorter than the last 2 we have done. So let's read what we're given here. We are given the total work required to stretch a spring from its equilibrium to 5 meters past its equilibrium is 400 joules. Now let me just write down what we're told so far. It's a work. We know work is integral. So this would be an integral from 0 to 5 of something is 400. This is what we're given. And then we want to find the spring constant K. Now, before I fill this in, let me finish reading the question, because it says you may assume Hooke's law applies. And so Hooke's law, maybe I will remind us what this says. Hooke's law is a statement about force. It says the force, well, required to hold a spring stretched x units past equilibrium is f of x equals kx, where k bigger than 0 is the spring constant. So I didn't write the whole statement of it. I just wrote enough so we can do the problem. But Hooke's law is a statement about force. That's an important thing to understand. And then we are given a work. We have variable force. So work is just the integral of force. So that's what I'm going to put here. Then this is given. And then the question is, find the spring constant K. Wonderful. All we need to do is just integrate this, evaluate between 0 and 5, and then we set that equal to 400, will allow us to find the spring constant. So the left-hand side, this is K, x squared over 2. And then we evaluate between 0 and 5. And this is supposed to equal 400. This is given. And we can do one more step. This would be 25 over 2 K minus 0 is 400. Now we can just multiply by 2 and divide by 25. So my spring constant is 800 over 25, which is 4 times 8. This is 32. This is my final answer here. You see, this was a lot shorter than our pumping problems, but it used Hooke's law. Now we move on to the multivariable questions on our quiz extra practice. The first one is number 4. We are given 2 points, P and Q. These are in R2. The first one, we want to find this displacement vector, vector PQ. So how we calculate this is, well, you take the entries of Q minus the entries of P. So this would be 3 minus 5, minus 1, minus 4. And you see this is -2, -5. Letter B, we want to find 2 vectors parallel to PQ that have length 6. Well, the first thing I need to do is figure out what is the length of vector PQ. And so vector PQ has length, well, you take the square root and then you square each component. So this would be 4 plus 25. This is the square root of 29. And we leave it like this. Don't put this in your calculator and get a decimal approximation. What this means is if you take PQ, this vector, and you divide by this, this will be a vector that is unit. I'm going to use that now because let me take here -2, -5, and take 1 over this. This is unit. If I put a 1 up here, I put a 1 here. This is unit. So how do I get a vector of length 6? Well, one option is just multiply this by 6. Let me copy and paste, okay, because I need 2 of them, like I said. One is just multiply by 6. There is a vector. Certainly, it's parallel to PQ because here's the multiplier. It's a multiple of PQ. But then also the way we constructed it, this vector has length 6. Another one is take this unit vector and multiply by -6. So here's our 2 vectors. Here's one and here's the other. They are parallel to PQ and have length 6. Now we have a question from dot product and orthogonal projection. We're given 2 vectors in R3, V and W, and we want to do multiple things. Letter A, we want to find V dot W. We take V dot W. This would be 2 times 2 plus 0 times -5 plus 1 times 3. And then we notice this is 4 plus 3, this is 7. Now, immediately, before I even answer letter C, I know the answer to letter B because this is positive. And so this says that the angle between V and W is acute. So let's move on to letter C. Find the angle between these 2 vectors. We can leave cosine inverse in our answer. Well, we have the dot product. Maybe I should underline this. We have the dot product. And all I need to do now is calculate the length of V, calculate the length of W, and then I know that theta will be cosine inverse of, well, it will be as V dot W, as we will see, but I'll go ahead and write it here, divided by length of V times length of W. Okay, the length of V, just like we saw in the last example in R2, we take and square each component, add them up, and then we take a square root. So this is 4 plus 0 plus 1. The length of V is the square root of 5. Once again, leave it like this. You don't want to type that into your calculator and get an approximation. Length of W, we take the square root. This would be 4 plus 25 plus 9. This is the square root. Let's see, we have 34 plus 4. This is square root of 38. So now I'm ready to just write this down. This would be cosine inverse of v dot w, which is 7, divided by length of v times length of w, which would be here, square root of 5 times square root of 38. This is our answer here. Now we want letter D. We want to project W onto V. Let's write the formula, but really we don't have very much to calculate because we've already done a lot of this work. So if we project onto V vector W, this will be, it will be W dot V divided by V dot V. This is the multiplier. And then times vector V. So you see, this is definitely a multiple of V. And then as we discussed in class, this multiple is chosen so that, let's see, if you take W minus the projection, it's perpendicular to V. But we don't have to rederive how we got that formula each time. We can just use it. So you see, I already have W dot V, and in a way, I already have V dot V. But maybe I'll write this down. V dot V, I'll just write it again. V dot V we know is the length of V squared, but I will just write it again. It's fine. V dot V is 4 plus 1, which is 5. So this is, we have V dot W or W dot V. They are the same thing. So this is 7 over 5. And then times vector V, which is 2, 0, 1. This is a perfectly fine answer. Just like in number 4, it was okay to leave our sort of coefficient on in front. You could also write this as 14 over 5, 0, and 7 over 5. Either one is perfect. It's the same vector. So either one. Either is okay. This is the end of number 5. Number 6, this is the last one on our quiz extra practice. It's incredibly short. In fact, it's kind of just using the definition, but this comes from our lines and planes section. We want an equation of the line in R3 that contains this point, 7, 3 minus 10, and is parallel to this line. And I'll give the equation in vector form. So as we look at this, we can read off a vector that's parallel to the line, and we can see it here, here, and here. So V, which is 12, 3, negative 5, this is parallel to the line. Not only the given line, but the line that we want, right? This is because we want a line parallel to this line and containing this point. And so let's just write it down. An equation of the line I am interested in would be XYZ equals, we have 7, 3, negative 10 plus T times 12, 3, negative 5. You can leave it like this. You could also add these two vectors and have it more in this form. I'll just leave it like this. It's a perfectly fine answer. This is the end of quiz 6 extra practice. Thank you so much. Good luck on the quiz.